case. The Mach number in crystal condition should be around 0.2. The grids are always here. In Moodle, you can find this def file that we will use to import the mesh in Fluent. So you can download this file. This is exactly the same than last week. And that's it. Well, if you have the last week case, it's even easier. You can actually load that in Fluent. You can actually import it or read it in Fluent, and you just need to change the turbulence model. Right now, I'm showing you how to set up again the case from scratch, but it's basically straightforward. If you have that ready, then you just need to change the turbulence model to a one equation turbulence model. Okay, so I think we can start with the solver. For last week, I also uploaded problem 5, in the problem 5 folder, PDF here that shows more or less all the step-by-step how to set up the case, and also some description how to post-processing. So that's useful also, let's say, for today's exercise. You can follow except the step of the turbulence model. Then that is different. Okay, so I have here my working folder where I copy the def file. So I'll open Fluent. And in the Fluent launcher, I need to set the working directory. So I'll just copy this path in the working directory. These are always 3D cases, even though they are quasi 2D, but these are still solved like 3D cases in Fluent. Double precision, and then solver processes I use 3. So I can start the software. So as a first thing, I upload the def file, that is the geometry and the mesh file. So from file, import, this is a CFX generated file. So I need to select this CFX definition file. And there I can select the def file that I want, so the one that you can find in Moodle, and read it. Once it's loaded, I typically check that the case is correct. So I hit display in the general tab. Then I also select the edges to show the mesh lines, and then display. So you can see that here the case is loaded, and also the mesh seems good. You can also see that every surface has a different color depending on the actual boundary layer that is set. So well, I'm colorblind, so I don't trust let's say, the colors that I say, but this is somewhat blue. Then here so this is the inlet, the outlet is red. Then here we have some yellow, this is the symmetries. And then there is this gray, this is the wall. So you can already check what are the boundary conditions there. So as a first thing, I define the material. So this is a fluid region. There is no solid except for the boundary conditions at the plate. So in materials, I need to set. So I double click on materials, and in fluid, I can change the air model. I change the density from constant to ideal gas. So that depends on pressure and temperature in the domain. change create. Then in Fluent you always have to hit change create in order to save, let's say, the settings that you are modifying. Next, now we go in the turbulence models. We need to set the turbulence, the viscous model. So in models, now the energy is on because this is an ideal gas. So it needs the temperature calculation. And in viscous, now we have the SST K omega by default. And we were asked to simulate this case with a one equation model. And we have this Palartal-Maras one equation model here. So we can select that. We have some options, but we don't need to enable these options for this case. And there is also a production term we can choose if we want a vorticity based or string vorticity based. We are going with the default one, the vorticity based. So if you want to know more about, let's say, the theory of these models or how they are implemented in Fluent, now select OK here. There is this very useful theory guide that you can access from hitting the Help button on the top. And there is user's guide on contents. So if you go from there, you will be redirected to a browser page. Okay, so where you can search here in what you are interested to. So for example, here we have this search for Palartal-Maras. So I want to know more how this is implemented in Fluent. So what are the equations that is solving? What are the constants that are set? By default, Fluent is applying a filter, so it's only looking for the results related to the Fluent user guide. I'm going to cancel that so that I can also find the results for the theory guide. So here you see that the second result is the theory guide related to this Palartal-Maras model. So if I select that, here I can check all the options. So the overview, a general description of this Palartal-Maras, what are, for example, the Y plus treatment. So when you use turbulence model, one important thing is also the grid that you are using, that you should be able to solve the boundary layer. So close to the wall, you need fine grid. Right now, we are not really doing that, so we are taking like ready-made grids from online. But it's something that that is important when you are choosing the turbulence model, that you are able to solve the boundary layer region. So close to the wall, that you need some fine resolution. Here you have some information about what kind of grid you need for that model. And then something that you have seen during lecture, so you also have some suggestion how you should use this model. So for example, this is quite useful for aerodynamic flows. And then here you have also the transport equation. So the solver will be solving this equation where the variable here that you are solving for is this nu, that is the eddy viscosity, or something related to the eddy viscosity. And you can also find then more information about this variable that is solved, how it's related to the turbulent viscosity. Actually, that is the one that we need, and also some other information about the source terms if you are interested. Of course, for running the case, we don't really need to know all of this information. You can run it without knowing. That's, let's say, for your, if you are curious to know that, up to you. So we can just select it and we have it there. Of course, in that user guide content, you can find basically everything about Fluent, almost everything. For example, I couldn't find any information about the mixing length. That was kind of secret. Okay, then the next thing I'm gonna do is to set the cell zone conditions. I double click that, And I'm changing the operating conditions on the bottom. There is this operating pressure, so I set this to 0, so that the absolute pressure is equal to the gauge pressure. So set zone conditions, operating pressure to 0. That's it in set zone conditions. And then the next thing we can do is in boundary conditions. We can set the boundary, so the ones that are shown there. So the far field is the surface at the top, farther away from the plate. This is asymmetry. We set it like asymmetry, so it's by default already here asymmetry. Inlet, it's set as a velocity inlet, but we know the total pressure and total temperature there, so we change the type of this to pressure inlet. And so we set as a gauge total pressure the value over there that is 1.02828 bar, so E5, that means 10 to the power of 5. And I copy this value also for the initial good pressure. So when I'm initializing the solution, Fluent is using that value as a initial gauge pressure at the inlet. And I hit apply. Now you can see that here we have also a boundary condition for the turbulence. We don't really need to change that. We can leave it as default. You can set either the turbulent viscosity ratio, that is the ratio between the turbulent viscosity and the molecular viscosity. Or you can also, if you have some other information about the flow at the inlet, you can set it here. But typically this is unless you are sure that you want to set that kind of boundary condition for the turbulence, you leave it by default. Unless you are having like some measurements at the inlet, so you want to set exactly that level of turbulence, otherwise not very important, I would say. So I hit apply. Then in the thermal, the total temperature is 300 Kelvin, so that's correct, so we don't need to change that. And so I close that window. Then the next boundary condition that we need to set is at the outlet. So we have a static pressure at the outlet that is 1 bar. So this is already a pressure outlet type, but we need to change the magnitude of the static pressure. So we add it, and the gauge pressure, this is still in Pascal, so it's 10 to the power of 5, that is 1 bar. And that's it. Other boundary conditions are for backflow. So if in case there is some flow that is going in the negative direction, that's not our case, so we don't really need to care about this backflow boundary conditions. And apply. Alright, then in plate, this is a adiabatic no-slip wall. By default, Fluent sets wall as no-slip, and also in thermal, the net heat flux is 0, so that means adiabatic, so we don't need to change the one for the plate. Then we have symmetry. Symmetry are these two surfaces on the right and the left sides of the domain, since this is a quasi 2D case, so 3D, and we can leave them like symmetries. And then finally, symmetry inlet, that is that small surface at the beginning of the domain. And last week we set it like a slip wall, because for the mixing length model, that if we set it like a symmetry, it was having some issues. But this time, this turbulence model, we can leave it like a symmetry, and it's going to work fine. So we don't need to change that. Then next thing we can do is in methods. Now we have the default settings that we didn't change last week. So I'm running with this coupled scheme, and there is a global time step. That is that there is a transient term also in the governing equations that you are solving. The only thing that I change is the scheme for the turbulent viscosity. So we see that all the other variables are solved with a second order upwind, but the modified turbulent viscosity with a first order. We can select also for that a second order upwind. That means more accurate result. Typically, if you enhance, if you increase the order of the numerical scheme, you may have some divergence problem depending on your case. So it's but in second order you get more accurate result. So in this case we won't get any divergence or numerical problems, so we can select the second order outcome. Then in controls, we can leave it by default. These are also parameters that if you encounter some numerical instabilities, these relaxation factors can help to get convergent results if you have the problem is, let's say, numerically difficult to converge. But this is not the case, so we leave them like they are. And then in monitors, if you expand monitors, here you have residual. If you double click, here you can set the criteria that you want to set for having a convergent solution. So how low the residuals have to be. Last week we set them to 10 to the power of -5. So 1 in -5, and I'm doing the same for all of them. So I set them all of them to 10 to the power -5. And okay. So we set everything we needed to. So now we can initialize the problem. So we go in the initialization, and we choose the hybrid initialization, so we can initialize. So we let Fluent do the initialization part. So when it's done, we have already one, let's say, initial solution. At least each cell has a value for every flow variable. And then we can go and run calculation, where we can set the time scale factor. Also this value here, you can adjust it if you see that you have numerical difficulties to converge. That means that you are reducing the time step. So the solution is applying a lower time step to get to the steady state solution, because we are still solving for a steady state problem. And then we can leave it to 1 for this case. And for number of iterations, I set it to 1000. We'll need less than 1000. So when our residuals we set, so 10 to the power -5, they are met, then the solution is stopping, the solver is stopping. So we can calculate after that. Were you all able to set up the case? Yeah. Okay.